This call is now being recorded.
Okay, once again, good afternoon, everyone. We are now on chapter 8, hypothesis testing. So, in chapter 7, we actually studied a method of inference called point estimation. Now, let's proceed to another method called the hypothesis testing. So, to start, let us define a hypothesis. So, we have here a hypothesis is a statement about a population parameter. In other words, a hypothesis makes a statement about the population. So the goal of a hypothesis test is to decide based on the sample or the information that we get from the sample from the population uh, and to decide which of these two complementary hypotheses is true. So we have two complementary hypotheses. The first one is called the null hypothesis, and then the other one is called the alternative hypothesis, and they are denoted as H sub 0 and H sub 1 respectively. So if theta denotes our population parameter, okay, so we have here a general format for the null and alternative hypothesis. So for our null hypothesis, we have H sub 0. We have this statement that theta is an element of a big theta sub 0. This big theta sub 0 is what we call the null parameter space. And then the alternative hypothesis, H sub 1, is the statement that theta is an element of big theta sub 0 complement, C, to the C. Or in other words, this is the complement of big theta sub 0, or we can also call it as the alternative parameter space. So if we're going to take the union of the null parameter space here, this is the null parameter space, this is the alternative parameter space, then we have the entire parameter space. Okay, so that's our entire parameter space. So we have an example here. If our parameter theta denotes the average change in the patient's blood pressure after taking a drug, so an experimenter might be interested in testing the null hypothesis that this parameter theta is equal to 0 versus the alternative H sub 1 that theta is not equal to 0. So the null hypothesis states that on the average, when theta is equal to 0, so the drug has no effect on the blood pressure. Take note that our theta is the average change in the patient's blood pressure. So if it is equal to 0, then the drug has no effect on blood pressure. And the alternative hypothesis states that there is some effect. So this common situation in which the null hypothesis states that the treatment has no effect has led to the term null hypothesis. Okay? Or in this particular case here, in which our null hypothesis is a single, now we have a single statement, no? A single null hypothesis, and our test is actually a two-sided test, because if we're going to look at our alternative hypothesis, we have two possible area for our theta not equal to 0. It could be theta greater than 0 or theta to be less than 0. So our null hypothesis here is a simple null, and we have a two-sided test. If in a hypothesis testing problem, after observing the sample, the experimenter must decide either to accept the null hypothesis as true, okay, or we fail to reject our null hypothesis, or to reject our null hypothesis as false and then decide that the alternative hypothesis H sub 1 is true. Okay, that is our in our hypothesis testing procedure, testing problem procedure. So, rather, a hypothesis testing procedure or hypothesis test is a rule that specifies 1I, for which sample values the decision is made to accept the null hypothesis as true. 2I, for which sample values the null hypothesis is rejected and the alternative hypothesis is accepted as true. So the subset of a sample space for which the null hypothesis is rejected or will be rejected is called the rejection region or critical region, while the complement of the rejection region is called the acceptance region. So in a hypothesis test, the test is usually specified in terms of the statistic. We have a function of the sample. Here we denote it as W of our sample. Say, for example, we have a test that we might specify that our null hypothesis H sub 0 is to be rejected if the sample mean is greater than 3. So in this case, our test statistic here is our sample mean. And then if we're going to consider the rejection region, it is the set of all sample points. Okay, so we have here our sample point, the set of all sample points such that the estimate of our estimator, which is the small x bar, to be greater than 3. So in section 8.2, we're going to consider methods of choosing the test statistics and rejection regions. And then in section 8.3, the criteria for evaluating these tests. So let's proceed now to section 2, methods of finding tests. The first one, we have the likelihood ratio test. So the likelihood ratio method of hypothesis testing is related to the maximum likelihood estimators discussed in section 7.2.2. And then the likelihood ratio tests are as widely applicable as maximum likelihood estimation. Recall that if we have a random sample or these random variables x sub 1 up to x sub n from a population with PDF or PMF, a small f of x given our parameter theta, this theta may be a vector. So the likelihood function is defined as the function of our parameter theta given our sample. So in this case, we fix our sample, and the one who is variable here in the likelihood function is our parameter theta. And this is equal to the joint density of our random sample. And that would be equal to the product of the densities, f of x sub I given theta I from 1 up to n. So we denote this, big theta to the entire parameter space. Let us now define the likelihood ratio test statistic for testing the null hypothesis that our parameter theta is an element of the null parameter space big theta sub 0 versus the alternative that theta is an element of the alternative parameter space, big theta sub 0 complement. And this statistic is being denoted as lambda of our sample point x. So lambda of x, it is equal to this fractional expression. We have the supremum of the likelihood function of theta given our sample x over the null parameter space divided by the supremum of the likelihood function of our parameter theta given x. The supremum is over the entire parameter space. Okay, so the likelihood ratio test is any test that has a rejection region of the form. So this is the set of all sample points, bold small x, such that the likelihood ratio test statistic lambda of x is less than or equal to c, where c is any number satisfying C greater than or equal to 0 but less than or equal to 1. So this is our working formula here in our definition in computing for the likelihood ratio test statistic. So if we think of doing maximization over both the entire parameter space, when we consider the entire parameter space, we have an unrestricted maximization and a subset of the parameter space. Here we actually consider the null parameter space and we consider a restricted maximization. Then the correspondence between the likelihood ratio tests and the maximum likelihood estimators become more clear. Suppose that if we have theta hat here, the maximum likelihood estimate of our parameter theta exists, and theta hat is obtained by doing the unrestricted maximization over the likelihood function. Then we can also consider another maximum likelihood estimate of our parameter theta. We call it as theta sub 0, and we obtain this by doing a restricted maximization actually over the null parameter space. So that is the theta hat sub 0. It is the value of, the value of our unknown parameter theta in our null parameter space that would maximize our likelihood function. Then we have an alternative likelihood ratio test statistic. This is now in terms of the maximum likelihood estimates. So we have lambda of x to be equal to this fractional expression. We have now the likelihood function of a theta sub 0 hat given our sample x divided by the likelihood function of theta hat given our sample point x. Take note of this, that this theta sub 0 hat, this is the maximum likelihood estimate of our parameter theta when we're doing a restricted maximization. For a restricted maximization. While the theta hat, this is the MLE of our parameter theta over all the parameter space of big theta. That is why this is unrestricted. So looking at the two, formula in our definition and this remark, if we can use the formula if we do not know the maximum likelihood estimate for our likelihood function. But if we knew already the likelihood function, or rather we knew already the maximum likelihood estimate of our parameter, then we can use the alternative formula. Let us consider example 8.2.2 to illustrate especially the definition as well as the alternative formula. The conditions below, or rather the examples below. So let x sub 1 up to x sub n be a random sample from a normal population with mean theta, and then the variance is equal to 1. And then consider testing the null hypothesis that theta is equal to theta sub 0 versus the alternative that theta is not equal to theta sub 0. Looking at our null hypothesis, it is a simple null hypothesis. And looking at our test, it is actually a two-sided test. So here our theta sub 0 is a number fixed by the experimenter prior to the experiment. And since we have only one value of theta in our null parameter space specified by our null hypothesis, then the supremum of the likelihood function over the entire null parameter space will simply will only contain this value theta sub 0. That is why the numerator of our likelihood ratio test statistic will simply be this. No, ang supremum lahat, isa lang naman yung element ng ating null parameter space. Then we have here the likelihood function of theta sub 0 given x. And then in example 7.2.5, we were able to get the maximum likelihood estimate of our parameter theta, which is actually the sample mean. We have that in example 7.2.5. Thus, the numerator, rather the denominator of our likelihood ratio statistic will simply be L of the sample mean x bar given our sample. Okay, so the likelihood ratio test statistic is, okay, so we have this. Pwede natin isulat yung numerator natin. We have L of theta sub 0 given our sample x. And then the likelihood function using the maximum likelihood estimate x bar given our sample x. Okay, ang reason natin dito kasi yung sa null hypothesis natin, isa lang yung kanyang element. Here. And then ang denominator, we have considered the maximum likelihood estimate of our parameter theta, which is the sample mean. Okay, so lambda of x, if we're going to consider our likelihood function, then we have here 2 pi raised to the negative n over 2, the exponential function of the negative summation. Okay, note muna na lang natin para malaman yung likelihood function natin when we have our parameter theta given our sample x. This is equal to 2 pi raised to, since our variance is 1, so kaya 2 pi lang, no? Negative n over 2. We have here the exponential function of the negative. So we have here the summation I from 1 up to n. And you have here xi minus theta square over 2. So we just replace our theta here. No? Ito, replace this theta by theta sub 0 in the numerator and replace theta by x bar in our denominator. Okay, so we have that. So that means that we can cancel this. And then using the law of exponents, so we have here the exponential of the negative. Okay, we have that. It can easily be verified. And then considering this expression here, this summation, no, of the square of x sub I minus theta will be equal to this expression on the right hand side. We simply subtract the sample mean, and then we add also the sample mean. Okay, we have that. And then expanding it, we have actually 3 terms, but the final answer will consist only 2 terms because of the fact that the mean, yung sa middle term natin, pag-expand natin yan, yung middle term natin, we have this, the x sub I minus x bar is actually equal to 0. Okay? So mawala yung middle term, yung sa last term natin here. Okay, it does not depend on the index of our summation. So that is why we have an n here. N times the square of x bar minus theta sub 0. So that's our result. So if we're going to substitute this expression now, here, so mag-cancel itong summation of the square of x sub I minus x bar. So yung maiiwan, ito na lang yung maiiwan sa expression natin above. That is why the likelihood ratio test statistic, we have here lambda of x. Okay, the lambda of x is equal to the exponential of negative n times the square of x bar minus theta sub 0 over 2. Okay, madali lang naman yan. You just substitute this expression, no? Itong expression na to, you just substitute it here. So, mahimo siyang negative summation and then natay negative na din ang result yan sa n times x bar minus theta sub 0 quantity square. Okay, so we have already computed our likelihood ratio test statistic. Now, we're going to determine the rejection region of our test. So our rejection region is the set of all sample point, bold small x, such that lambda of x is less than or equal to c, where c has a value between 0 and 1 inclusive. And it can be written as, no? It can be written as this, the set of all sample point x such that the absolute difference of the sample mean x bar minus theta sub 0 would be greater than or equal to the square root of negative 2 log of c over n. Okay? In other words, we have expressed our rejection region that contains the simpler statistic, you know? The absolute value of x bar minus theta sub 0. So, paano natin nakuha yan? Okay, we can have this notes. Ganito man yun. Kung gusto natin i-determine ang ating rejection region, it should be less than or equal to c. Pero, this lambda of x, it is equal to the exponential of negative n x bar minus theta sub 0 quantity square over 2, and this is less than or equal to c. Okay, so if we're going to apply logarithm to both sides, then we have negative n x bar minus theta sub 0 quantity square divided by 2 is less than or equal to the logarithm of c. Okay, we multiply both sides by 2. At the same time, we divide both sides by negative n. So we have here theta sub 0 quantity square. This would be now greater than or equal to. So the sense of inequality is being reversed. Okay, 2 pala. Negative 2 log of c over n. Okay, so we have here x bar minus theta sub 0 would be greater than or equal to the plus and minus the square root of negative 2 log of c over n. Or simply, we have the absolute value of x bar minus theta sub 0 is greater than or equal to the square root of negative 2 log of c over n. Okay, so we have this absolute value coming from our definition of the absolute value and the square root, no, the square root of the square. Yeah, parang ganito. We have here, say the absolute value of an expression is equal to positive e if e is greater than or equal to 0, negative e if e is less than 0. Same thing with the square root of an expression square. It will be equal to e if e is greater than or equal to 0, but negative e if e is less than 0. So, nakakay positive and negative diana, no? Kani, the square root. So, the answer for that, kung consider natin yung e, here, we have the plus and minus square root. Ipabaliktad mo na yan. So we have the plus and minus the square root of e squared. Okay, so that would be just equal to the absolute value of an expression. So ito rin yung nakuha natin. Okay, so this would imply, okay, this would imply now, so the rejection region set of all x such that lambda of x is less than or equal to c would be equal to the set of all sample point x such that the absolute value of x bar minus theta sub 0 would be greater than or equal to the square root of negative 2 log of c over a. Okay? So for this example, we applied our remark for the likelihood ratio test statistic in which dito sa actually in which yung maximum likelihood estimate, we apply it on the denominator of our likelihood ratio test statistic because we have an unrestricted maximization there. But in our numerator, sa numerator natin sa ating lambda of x, we simply look at the supremum of the likelihood function over the entire null parameter space. But since our null parameter space contains only theta sub 0, so there is no other value of theta that would maximize the likelihood except theta sub 0. Kaya ito yung nakuha natin na expression. Ito. Okay, any questions or clarifications? Pagkuha pa lang ng likelihood ratio test statistic at the same time yung critical region. None so far?
Yes, sir, none, sir.
Okay, let's proceed to the next example. We consider the exponential likelihood ratio test. Let x sub 1 up to x sub n be a random sample from an exponential population with this PDF. F of x given theta e to the negative x, the quantity x minus theta if our x is greater than or equal to theta and 0 otherwise, where we consider theta to be greater than negative infinity but less than infinity. In other words, yung ating entire parameter space here is the real line. Okay? The entire parameter space theta in the entire parameter space is the set of real numbers. So the likelihood function is this, okay, in which the x sub 1, the minimum order stat, based on our factorization criterion, it's actually the sufficient statistic. It's actually the sufficient statistic. So, pagkuha naman yan, the likelihood function, okay, of our parameter theta given our sample. So we have here the product of e to the negative xi minus theta I from 1 up to n. Here the xi is greater than or equal to theta, and then 0 otherwise. Okay, say the product of that would be equal to e to the negative summation of x sub I minus theta I from 1 up to n. And then here, still xi is greater than, and then 0 otherwise. Okay? Furthermore, we distribute the summation. Then theta does not depend on the index of the summation. Then we have here e to the negative summation of xi, I from 1 up to n. And then we have here plus n theta. And then 0 here. Theta, okay? So, xi is greater than or equal to theta, then xi is less than theta. Okay, so yung mga xi natin greater than or equal to theta, so that would also imply that the minimum order stat, the minimum of all the sample points x sub 1 up to x sub n, no, would be greater than or equal to theta. So pwede natin itong sabihin nilang, we have here e to the negative summation of x sub I from 1 up to n, plus n theta. So pwede na lang sabihin natin that x, the first order stat is greater than or equal to theta, 0, and then 0. Okay? Yan. Nakuha natin to, yung ating likelihood function. Okay. Consider now testing the null hypothesis that theta is less than or equal to theta sub 0 versus the alternative that theta is equal to is greater than theta sub 0, where theta sub 0 is a value specified by the experimenter. Okay. In this case, it's so hard to determine the maximum of this by differentiating our likelihood function. But let us try to look at the graph of our likelihood function, and we can see that the likelihood function is actually increasing function of theta on this interval, negative infinity up to the minimum, the first order statistic, the minimum order statistic. So exponential man yung ating likelihood function, obviously, ganito yung graph niya. Pwede natin sabihin, ito yung graph niya. Okay, so say this is for our theta. Ayan. Yan na lang natin. So for this point, say we have here the minimum order stats. It will be 0 after this. Yeah, it's a whole. And then we have this point. Okay. So this is actually the function, our function, the likelihood function. The likelihood function. Lagyan ko lang ng y, ha. The y here could either be the exponential of the summation of x sub I plus n theta, or it could be 0. It depends on the value of our theta. Okay? Kasi pag ang minimum order stat is less than theta, ito na yung graph niya. Ito na yung graph niya. Below, ayan niya. 0 siya entire. Pero when theta is below or less than, it's less than the minimum order statistic. So we have an increasing function for our likelihood function. Likelihood function of our parameter theta. So this is clear. No? It is an increasing function of theta on, dito yan na interval. Dito na part. Ito. This is from negative infinity less than theta less than or equal to. Ito na part, no? Ayan. It's an increasing function. Okay? So, parang kulang yung space ba? It's an increasing function. So if we're going to look at the denominator, kung titingnan natin yung denominator ng ating likelihood ratio statistic, lambda of x, over the entire parameter space, from negative infinity to positive infinity, saan ma-maximize yung ating likelihood function? In other words, the supremum, yung supremum of the likelihood function given our sample x over the entire parameter space. Yun, ganun. Over the entire parameter space. Kung titingnan mo yung blue na graph, this likelihood function will reach it, no? It will be maximized when our theta is equal to theta, the minimum, when theta is equal to the minimum order stat. Kaya, sabihin natin, this will just be equal to the likelihood of the minimum order stat given our sample. Okay? Bold yan siya. Yan yung denominator ng ating likelihood ratio test statistic. What about yung numerator niya? Ano yung numerator ng lambda of x? Okay, sabi dito, it is the supremum of the likelihood. Ginamit natin yung definition dito. Kasi yung first example, ginamit natin yung remark. Ito, ginamit natin yung definition. So we have here theta given our sample x on the, okay? On the null parameter space. Ano yung sa null parameter space natin? That theta is less than or equal to theta sub 0. Ngayon, kung titingnan natin to, this would be equal to what? Kunwari, says there, no? Theta is less than or equal to theta sub 0. So, kunwari, dito yung theta sub 0 natin. Our theta sub 0 falls on this. Okay? When theta so, if our theta sub 0 falls on this part, dito siya na part, that would mean, it means that theta sub 0 is less than or equal to the minimum order stat x sub quantity 1. Makikita naman sa graph, no? Mas maliit yung theta sub 0 sa x sub quantity 1. So in other words, kung titingnan mo yung graph, ito yung maximum niya. Dito yung maximum niya. So that means that we have what we have. The likelihood function of theta sub 0 given our sample x if, now we have the condition that if theta sub 0 is less than or equal to the minimum order stat. Ito naman, kung nandito yung ating theta sub 0, so that means that the minimum order stat is less than theta sub 0 or theta sub 0 is greater than the minimum order stat x sub quantity 1. Pero kung titingnan mo yung graph na blue, saan siya na ma-maximize yung anong value ng theta na ma-maximize yung ating likelihood function? Nasa minimum order stat. That's why we have here the likelihood. Kung titingnan natin yung blue na graph, we have here x sub quantity 1 given our sample. If this time, the theta sub 0 is greater than ayan. Okay? So we have that. So if we're going to compute for our lambda of x, kasi dito binigyan na tayo, critical region lang ang nilagay dito. This is our critical region. Pero paano natin i-compute yung ating likelihood ratio test statistic, lambda of x? So lambda of x here would be equal to, yun, dalawa, no? Numerator, denominator. So ano yung ating numerator? Dalawa, no? We have here. Ang numerator natin, we have the likelihood x sub 1 given x. Okay? Yung denominator natin, the likelihood function of theta sub 0 given x. This is for the case what? If theta sub 0 is less than or equal to first order stat. Or we may have, siguro, ibahin ko na lang, the likelihood function of x sub quantity 1 given x. Kasi yan pa rin yung ating baliktad pala. Kabaliktad, sorry. Numerator, denominator. Sorry masyado. Erase. Red muna. So the likelihood, numerator tayo, theta sub 0 given x divided by, yung denominator isa lang, no? So quantity 1 given x. Okay? Yung pangalawa, blue na lang, the likelihood of x sub quantity 1 given x given x. This is what? If theta sub 0 is greater than or sub quantity 1. Okay, sample. Yan. Okay, so this would be equal to 1 na yung sa denominator natin. Yung sa isang part. Yung sa blue. Ito 1. This is if what about in our red na part? Sa red na part. Ano yung ating likelihood function in that case? So we have here the exponential. Kulang lang yung itong kanan. Ano yung exponential natin sa itaas? EXP na lang, no? The exponential of the negative n up, sorry. Oh no. Okay, so we have here the negative summation of x sub I plus n theta sub 0. Kasi theta sub 0 yun siya. And then divided by the exponential of negative summation of x sub I plus n x sub quantity 1. This is if theta sub 0 sub 1. Okay, so simplifying it, that would be equal to, sa numerator tayo, sa itaas yung sa red na part. So, exponential. So, yung maiwan na lang, we have here the exponential of a positive n theta sub 0 minus n of the first order step if here theta sub 0 less than or equal to the sub quantity 1. And for the blue, it's equal to 1 if theta sub 0 greater than. Okay, so simplify further. Then we have here e exponential of n, negative n na lang. Then we have x sub quantity 1 minus theta sub 0. This is if theta sub 0 is less than. And then sa blue, 1 if theta sub 0. Okay. So this is actually our likelihood ratio test statistic. Hindi naman niya pinakita no, sa book, hindi naman pinakita. Ano yung likelihood ratio test statistic? What about the critical region? Ito lang binigay niya. Ito yung critical region. Itong part na to. Ito yung critical region. So the critical region, kulang na yung space natin. Dito na sa baba. Sa baba ko na lang isosolve yung critical region. Okay? So rejection region, gamay ra kaya kung nabutang na space. According to the likelihood ratio test statistic, it is the set of all sample point x such that lambda of x is less than or equal to c. Okay? That is, pwede natin i-compute natin yung ating lambda. Lambda of x less than or equal to c. If and only if. Okay? If and only if e to the negative n of x1 minus theta sub 0 is less than or equal to c. Okay, 1 man yun, no? Greater than, less than or equal to 1 yung isa, pero ito lang natin i-consider if and only if. Okay, if and only if. So we have here we have that. So we have here negative n quantity 1 minus theta sub 0 and the logarithm of c. If and only if. Okay, if and only if we have here negative na tayo. Nag-multiply tayo. So the sense of inequality is being reversed. Negative log of c over n. So if and only if we have here x sub quantity 1 is greater than or equal to. So we have here theta sub 0 minus a log of c over n. Okay? So, yung set of all lambda such x such that sample point x at lambda of x is less than or equal to c. This is the same as the set, okay, yun na, of all x such that x sub quantity 1 greater than or equal to theta sub 0 minus log of c over n. Okay, so yung green, shaded green sa itaas na rejection region, we were able to derive that using this inequality here. Okay, so any questions or clarifications?
Sir?
Yes, Nora Hanifa?
Sir, di ba gigamit na to ang sa isa ka example ang remarks dahil dire kay katong
Definition.
lambda of apo. Dahil unsa na mo pag-choose sir sa problem? Unsay gamiton?
Kani magud na problem sa second problem. It's so hard for us to determine the maximum likelihood estimate, no? Estimate of our likelihood of our parameter if we're going to differentiate our likelihood function. Because of the fact, no, kay kani nga to ang parameter theta here, na siya ang atong range, no? The range of our PDF includes our parameter theta. So naggamit lang tag maximum, not necessarily ang gi-check nato ang kanani ang graph sa atong likelihood function, and then we have seen indeed that the likelihood function is increasing on this particular interval of our theta. Itong part na to. Ito. Yung sa first example, if you can determine the maximum likelihood estimate, of your parameter, so it's easier to use the likelihood ratio test statistic in our remark.
Okay po, sir.
We have another.
Thank you po.
Yep, we have another remark here again. No? Say if P of X is a sufficient statistic for theta with PDF or PMF G of T given our parameter theta. So ito yung kanyang PDF or PMF. This is with respect to our sufficient statistic. Pag alam natin yung kanyang distribution, no? We know the distribution of our sufficient statistic. Pero pag hindi natin alam yung distribution ng sufficient statistic, hindi na lang natin gamitin itong remark na to. We have another technique. No? Then we might consider constructing the likelihood ratio test based on the sufficient statistic. And its likelihood function, ito yung likelihood function niya, denoted by L of star of our parameter given the estimate of our sufficient stat, which is small t, rather than on our sample. Having this likelihood function L of theta given our sample X. So if we let lambda star of t denote the likelihood ratio test statistic that is based on the sufficient statistic t, okay, it says here, given an intuitive notion that all of the information about our theta in X is contained in our sufficient statistic, because we know that the sufficient statistic contains all the information about our unknown parameter theta. So the test based on the sufficient statistic should be as good as the test based on the complete sample. So in fact, the tests are equivalent, and we state it with the following theorem. If P of X is a sufficient statistic for theta, then the likelihood ratio test statistic based on our sufficient statistic denoted as lambda star of t, and then the lambda of x are the likelihood ratio statistic based on the sufficient stat t and the sample x respectively, then these two. Itong dalawa pala, pareho, equal. Okay, these two. The lambda star of the sufficient stat t of x is equal to lambda of x for every x in our sample space. The proof of this is quite easy. No? It can easily be tracked. You can read the book for the proof of this theorem 8.2.4. Okay, so we're going to have another example here in which we're going to use the sufficient statistic. Okay, another technique ito LRT and sufficiency. So in example 8.22, we can recognize that the sample mean is a sufficient statistic for theta. Actually, we have also solved this when we are still on chapter 6. Na-determine natin that the sample mean is a sufficient statistic for our parameter theta when we have our random sample coming from a normal distribution. Merong condition dun, no? In which the variance is constant. Hindi siya no. So we could use the likelihood function associated with the sample mean. If we know, take note, as I have said, if we know the distribution of our sufficient stat. So in this case, the distribution of our sufficient stat X bar is normally distributed with mean theta, and the variance is sigma square over n. But yung sigma square natin sa example 8.2 to 1 man yun, yung variance natin dito. So 1 over n. Okay, so to more easily reach the conclusion that the likelihood ratio test statistic of this two-sided test rejects our null for large values of the absolute value of X bar minus theta sub 0. Ito, remark lang ito sa book. Wala ito siyang solution. Kaya papakita ko sa inyo paano ginawa na using the sufficient statistic. Okay? So, ito ngayon, ang solution yan. Okay, so, yung X bar, yung X bar natin, meron siya normally distributed with mean theta and variance 1 over n. So, yung ating likelihood, okay, yung likelihood function natin, based now on our sufficient statistic, okay, based now on the sufficient statistic would be equal to, ano yung likelihood natin? Based on our sufficient statistic. So we have 1 over the square root of 2 pi and then sigma square. Yung sigma square natin dito, kung siya, or sigma rather, over sigma. Hindi siya, kung sigma square nasa loob ng square root. Kung sigma square, pero kung nasa labas ng square root, we have sigma. What is sigma? We have the square root of 1 over n. Okay, 1 over n. And then we have here the exponential function of the negative of the sample mean minus theta divided by 2 sigma square. Pero ano yung sigma square natin? 1 over n. It is based on our statistic. No? Okay, so this is simply equal to the square root of n over 2 pi, the exponential negative n x bar minus theta over 2. Okay, so yan yung ating likelihood function based on our sufficient statistic. Now, if we're going to compute for the likelihood ratio test statistic based on our sufficient statistic, that is lambda star, okay, lambda star of our sufficient statistic, estimate of our sufficient statistic, so X bar. And we have here, it's actually the supremum of the likelihood function based tayo sa sufficient statistic of our theta given our sufficient statistic X bar, where theta here is an element of our null parameter space divided by the supremum of the likelihood function, okay, of theta given our sufficient statistic X bar, and theta element, no, this theta element of the entire parameter space. Okay, entire parameter space. So this is just equal to yung supremum ng likelihood function natin will just be equal to, kasi we have a simple, no, we have a simple null here. Take note, no, we have a simple null. So yung null hypothesis natin na big theta sub 0, it contains only theta sub 0. Yan lang yung nakalagay dyan. Isa lang naman. So this will just be equal to the likelihood of theta sub 0 given our sufficient statistic divided by gamitin natin ng maximum likelihood estimate for this case. Then we have here L star of the maximum likelihood estimate natin over the entire parameter space, yung likelihood function. We know it's the sample mean. Sa previous example natin, di ba? Ang MLE, X bar din. Sufficient statistic din yung X bar. Okay? So, simplifying, we have now square root of n, the exponential function of negative n x bar minus theta over 2 divided by, ano yung ating denominator when we consider the sample mean? No? When we consider the sample mean. So we still have square root of n over 2 pi. Ganun din. If we have the exponential, so negative n. So we have here x bar minus x bar over 2. This one will cancel out. And then this one will become 0. X bar minus x bar is 0. E to the 0 is 1. E to the 0 is 1. Then we have this final answer now. The exponential of negative n x bar minus theta over 2. Clearly, the lambda star of the based on our statistic x bar is equal to lambda of our sample x. Pwede ko ibalik sa first example natin. Ayan. Ito yung lambda of x. Exponential of negative n x bar minus theta sub 0 upon dt squared divided by 2. Dito, nakuha pa rin natin the exponential of negative n by square. Nakalimutan kong square pala. May square to. May square. Okay. Hindi nakita masyado yung square, no? Divided by 2. According to our theorem, the likelihood ratio test statistic based on our sufficient stat will be the same as the likelihood ratio test statistic based on our sample. Kaya explore niyo itong tatlo na method, no? Yung first example, we apply the maximum likelihood estimate, the remark. Yung second example natin, we apply our definition for the maximum likelihood, the likelihood ratio test statistic. And then itong third example natin dito, we apply this remark, no? Actually this theorem that we could able to find a sufficient statistic for our parameter, and we know, no, kung alam natin yung kanyang distribution. Gaya nito, sufficient statistic yung sample mean, then we know the distribution of that, then we can apply this theorem 8.2.4 for us to be able to determine the likelihood ratio test statistic. So yung critical region dito, pareho lang naman. Ganun din yung gagamitin mo. Yung critical region, same as above. Critical region to determine the critical region. Same procedure above. Hindi naman ito pinakita sa book, itong solution na to. Yun lang, sabi niya doon. Ito lang nakasulat yung example 8.2.5. Okay? So, para ito ha, take note of this. Lambda star tayo, hindi siya lambda. Lambda x. Kasi we base it on our sufficient statistic. So, given our sufficient statistic. Parang pareho lang naman sa definition pero not on the sample but based on the sufficient stat. Okay? Similarly, in example 8.2.3, okay, yung sa ating exponential function, ito lang yung sinulat sa book. Hindi na siya nag-verify. So you try. You try to. We know that the sample mean, rather the first order stat is also a sufficient stat. Pero alam nyo ba kung ano yung kanyang PDF ng first order stat? We have that in chapter 5 of STAT 331. Meron tayong formula niyan to determine for the PDF of our first order stat. So you try to verify this example using the sufficient statistic for our parameter theta. Okay? Any questions or clarifications? So anong gamit itong remark na to? Mas mapadali yung pag-determine nating likelihood ratio test statistic kung alam natin yung sufficient statistic at saka kung alam din natin yung kanyang distribution. Pero pag hindi natin alam yung distribution ng ating sufficient statistic, mahihirapan tayo na maghanap ng ating likelihood ratio test statistic. So mas mabuti pang gamitin yung remark where we apply the maximum, we determine the maximum likelihood estimate of our parameter over the null parameter space and over the entire parameter space yung sa denominator. Another, no? Ito pa sana, bago tayo sa pangalawang test, the likelihood ratio test are also useful in situations where there are nuisance parameters. That is, parameters that are present in the model but are not of direct inferential interest. So the presence of such nuisance parameters does not affect the LRT construction method, but as might be expected, the presence of nuisance parameters might lead to a different test. Tapusin na lang natin itong example na to. Then bukas na lang itong Bayesian test. So example, konti lang naman itong solution na to. Example 8.2.6, normal likelihood ratio test with unknown variance. So nuisance parameter itong variance kasi we are estimating our parameter mu, the mean. Hindi naman tayo nag-estimate ng variance, kundi yung mean. So suppose x sub 1 up to x sub n are random sample from a normal distribution with mean mu and variance sigma square, and an experimenter is interested only in inferences about the mean mu. So such as testing the null hypothesis that mu is less than or equal to mu sub 0 versus the alternative that mu is greater than mu sub 0. So we have a null hypothesis here, which is actually a composite statement. Okay, there are a lot of values of mu here in our parameter space, null parameter space rather. And then our test here is a one-sided test. So then the parameter sigma square is a nuisance parameter. So the likelihood ratio test statistic in this case is we have lambda of x is equal to this. Okay? we have the maximum of the likelihood function of our parameters mu and sigma square given our sample. By the way, ano kaya yung reason bakit hindi ginamit yung supremum, kundi yung maximum yung ginamit? Ayun sa definition natin, sup man siya, di ba? The supremum of all of the likelihood function where we consider the null parameter space for our numerator and the supremum of the likelihood function over the entire parameter space. Actually, halos wala naman silang kakaiba, yung maximum and supremum. But this time, ito na lang, it's the maximum. Ginamit natin yung maximum when we consider this given set, no? The set of mu and sigma square such that naka-embed dito yung ating parameter space. Na supposedly ito, no? Yung mu here is less than or equal to mu sub 0. So condition, the set of all mu sigma square condition that mu is less than or equal to mu sub 0. Nuisance parameter, sabi ko nga, no? That sigma square is greater than or non-negative. Yan naman yung assumption natin, no? Sa ating unknown variance. The maximum over the likelihood function. And then sa denominator, over the entire parameter space. Kaya ganun. Mu greater than negative infinity but less than infinity. So, ang mu natin over the entire parameter space. So, that's the likelihood function. Okay, so, since we know, alam natin ito sa chapter 6, if we're going to consider mu and the variance sigma square, both unknown, and if we're going to determine, we're going to determine the maximum likelihood estimate of this, na-apply natin ito before, we're able to show that the mu hat and sigma square hat are the maximum likelihood estimates of mu. Actually, meron itong corresponding, meron siyang corresponding expression. Itong mu hat natin is actually equal to the sample mean. Ito siya, meron siyang corresponding expression for sigma square hat. It's actually 1 over n, the summation of xi minus x bar quantity square. Okay, we have that. See in example 7.2.11. So, yun yung consider natin dito. We use the maximum likelihood estimates of mu and sigma square. Okay, so sa ating numerator, furthermore, if mu hat is less than or equal to mu sub 0, then the restricted maximum is the same as the unrestricted maximum. Ito para makita nyo i-graph natin. Say, ito yung graph ng ating likelihood function. Okay? Ito yung ating mean, no? Mu hat. Mu hats. So, kulang talaga yung space na nilagay ko. So, from here, pwede natin diretso dito. Kulang kasi yung space eh. Lambda of the sample x. Okay, this would be equal to okay, so say for example, nandito yung ating mu sub 0. Diba? Kasi sabi daw natin that our mu is less than or equal to mu sub 0. Kung nandiyan yung ating mu sub 0. So kung nandyan yung mu sub 0, ang value that would maximize our likelihood function, ito pa rin. Kasi mas maliit yung likelihood value dito sa mu sub 0. So that is why yung sa numerator natin will still have mu hat. So the likelihood function of what we have, mu hat, and then sigma sub 0 hat square given our sample x. Divided by, ano yung denominator natin? Pareho lang. Mu hat and then sigma square hat. Wala siyang sub-zero ha kasi over the entire parameter space. Ano nga ito? Yung condition natin dito, if your mu hat here, makita naman natin is less than or equal to mu sub 0. Diba? Dito pa rin siya. Ma-maximize yung ating likelihood function yung blue at this point sa mu hat pa rin. Pero, kung ang mu hat natin nandito, not mu hat, mu sub 0 nandyan. So, ibig sabihin yan na yung mu hat natin greater than mu sub 0. Okay, greater than mu sub 0. So, tapos, ang restriction natin, take note ha, itong restriction natin, yun, mu is less than or equal to mu sub 0. So, ito yung ating, kung ibig sabihin yan, sa violet tayo ha, ito yung area, ito yung region na, yan yung null parameter space. Kasi less than mu sub 0 siya. Less than mu sub 0. So, ma-maximize yung ating likelihood function dyan sa mu sub 0. Kaya ito, equal siya sa likelihood function. So, yung mu hat natin, ma-maximize yung likelihood function at mu sub, not theta sub 0, but mu sub 0. Okay, left to the mu sub 0. And then we have still sigma sub 0 hat square given our sample. Divided by, pareho pa rin ito, pareho pa rin yung ating denominator. Mu hat, sigma square hat given our sample. Okay? So obviously, yan, tama ito sa second part. Yung sa pangalawa, yung una, this is just equal to 1. That's why we have here. That's our likelihood ratio test statistic. If you want to, all the more, no, hindi naman nakasulat dito, all the more simplify this likelihood ratio test statistic. Ilagay nyo lang yung likelihood function natin dyan. And then masimplify nyo. And then further determine the rejection region for this particular case. Who knows? Baka lumabas yan sa exam. It's easy to verify naman kasi normal naman yan. And then determine also what's the critical region for this. Ito yun, for second, no? Ito, you just verify this. May napakita naman ako dito sa itaas. Ito yung example, when we have a normal distribution, ito sa exponential. Hindi na napakita yan sa book. So you try to show the solution to that. And all the more, simplify. Hanapin mo yung critical region dito. Critical region. To determine the critical region, you need to simplify this expression. Okay, guys?
Okay, sir.
Okay po.
So I hope na nakita nyo kung ba't nakuha natin yung lambda of x dyan, no? Take note always of our null parameter space. Itong shaded region dyan na orange. So may mga conditions dyan. Kung mu sub 0 mas malaki sa mu hat, so sa likelihood likelihood function natin yung blue, ma-maximize siya sa mu hat. Pero pag maliit yung mu sub 0 sa mu hat, so ma-maximize siya sa mu sub 0. Okay, so that's all for this afternoon. We started at 2 o'clock, supposedly na 1:30. So para na lang din na nagamit natin yung 30 minutes. So any questions or clarifications before we go? No questions here?
Wala, sir.
Okay, so tomorrow I'm going to discuss the second test, the Bayesian test, as well as the union intersection union test, and after that, evaluating this test. No. Okay, so I'm going to end now. Stop the recording. So